So my main area of research is an area called symplectic topology, and objects of interest are symplectic manifolds. So let me remind you that symplectic manifold is a smooth manifold, and endowed with the data of closed non-degenerate two-form, so two-form of maximal rank. And symplectic manifolds occur in many different contexts, but today I want to focus on a particular class of examples, which are interesting to me in particular because their study can be approached from many angles, and they involve different areas of mathematics. And these are so-called Liouville manifolds. So let me give the definition, and then I'll give some examples, and then I'll try to talk more about how these manifolds can be understood, studied. So the definition of a Liouville manifold is the following. So a Liouville manifold so it's a triple x omega Lie, where x omega is an open, necessarily open, symplectic manifold. And V is a vector field on X, satisfying the equation that the exterior derivative of the interior derivative of V with respect to omega gives back omega. And I also want to impose an additional condition, which I won't talk so much more about, which is that V is complete and exhausting. Complete means that the flow of V lives for all time, and exhausting means that you can exhaust your X by compact sets such that V is transverse to the boundary of these sets. Let me make a small remark which will be convenient, which is that once you've specified your symplectic manifold X omega, the data of this vector field, this Liouville vector field V, is actually equivalent to the data of a so-called Liouville one form, lambda, where lambda is just equal to interior multiplication V with respect to omega. So really, you can choose V, or you can give lambda. It's the same thing. Sometimes it's more. Question.
What does it mean, open symplectic manifold?
Oh, it means kind of not a closed manifold, so not a sphere. So I don't know, non-compact. It's exact, in fact. Oh, I haven't got an eraser. Use my hand. Okay, so let me give some examples to motivate this definition. So the first class of examples are cotangent bundles. So given n with smooth manifold, you can consider the cotangent bundle of n. And this admits a canonical symplectic structure. In fact, it admits a canonical Liouville structure. This lambda sub can is something which is canonical on the cotangent bundle. And you can write it, well, if you choose an open chart with coordinates q1 to qn, and and there are going to be canonical coordinates P1 to Pn on the fibers, which would allow you to write the Liouville vector field as something like a sum of Pi. Anyway, this doesn't really matter, but the main thing to keep in mind is that cotangent manifolds provide an important class of Liouville manifolds. So let me now mention a second example.
And what is the vector field in?
What is the vector field? So sorry. This is sum of Pi.
No, that's lambda, but in terms of the definition with a vector field.
No, this is also the vector.
No, but how to relate it?
Yes, they are related by this.
Yes.
So sorry, I'm not sure I understand the question.
I just want to know in this example, what is the vector field? Is it radial?
Yes, it's the one I've written down there. This is sum of Pi dPi.
Oh, that's not the lambda.
Yes, sorry about that. Yeah.
Sorry.
Okay. Yeah, it scales the fibers. Okay, so a second class of examples are smooth complex affine varieties. So let's let x inside C to the n be a smooth affine variety over the complex numbers, and I want to choose standard coordinates x1 plus iy1 xn plus iyn. And with respect to these coordinates, we can consider this, we can consider a one-form lambda, which is going to be defined as the sum over I of xi dy I minus yi dxi.
Would you like this eraser?
Well, thank you very much.
Omega in the second example?
I'm sorry?
What is omega in the second example? What is the form?
Oh, I haven't gone there yet, but it's just going to be the exterior derivative of it. Yeah, so given this data, we have a Liouville structure on X, which is given by the triple X, and then the exterior derivative of lambda restricted to X. And then our one form is just lambda itself restricted to X. And as I mentioned before, I've now erased that. This is equivalent to giving the data in the vector. And now the key fact is that this Liouville structure, which is really a structure living in symplectic geometry, is by a holomorphism. Invariant. So really the symplectic geometry, the symplectic topology of this structure is an invariant of the algebraic geometry, like of the complex. In fact, this phenomenon is more general. So there's a following theorem of Eli-Ashberg, which gives a third class of examples, which says that, in fact, any Stein manifold admits a canonical, this is up to equivalence, and I should have also said here, it's an invariant up to equivalence. Where the notion of equivalence is something I don't really want to get into, it's slightly complicated to say. Anyway, the theorem of Eli-Ashberg is that any Stein manifold admits a canonical Liouville structure. Right. So that's those are three examples, and now for the rest of the talk, I want to talk some more about the anatomy of these Liouville manifolds. So what perspectives can you take on these objects? So, anatomy of And really, I'm going to be describing so-called finite type Liouville manifolds. This is a technical condition which all of the previous examples satisfy. So I'd like to draw a picture. I guess I can draw it right here. It's a picture which one often draws, this area. Let's call it shot here. So this is my symplectic manifold. It's a two-dimensional symplectic manifold. And I'm going to start by drawing the Liouville flow on this manifold, which is represented by these arrows. Now, there's a certain subset of this manifold, which is defined as the set of points which never escape to infinity under the Liouville flow. So let's draw it in green. So I want to draw the flow a little bit more. Let's think of it. So this green subset is going to be represented as follows. It depends entirely on this Liouville vector field, and it has a name. It's called the skeleton. So the skeleton of x omega v is the set of points. Can people read the green from the back? No? Okay. Write it in white then. It's the set of points which don't escape to infinity. Okay, there's a second important set which is called the ideal boundary. I've drawn it in yellow here. It's a codimension 1 submanifold of the Liouville manifold, which is transverse to the flow and can be obtained completely canonically from the data of this Liouville manifold, and it's called the ideal boundary. This is usually written as follows, and you can in fact restrict the Liouville form to this set, to this canonical set, and you obtain something which is called a contact manifold, which is the main object of study in the area of contact geometry. So we started with this Liouville manifold, which is a symplectic manifold, and there are two objects that we obtained. We obtained this skeleton, which is this possibly singular set, and we obtained this ideal boundary, which is a contact manifold. And so the guiding question, I would say, at least in the study of Liouville manifolds, is somehow, how do these three areas interact? How does the symplectic topology of x omega lambda or x omega v interact with well, then you can ask various types of questions. The C0, the C infinity topology of the skeleton of scale x omega lambda, or in fact, also you can ask about the representation theory of the skeleton. In the sense which we'll talk about now. And finally, how does this interact with the contact topology of the ideal boundary? So have 2 more minutes. Let me end by stating some example theorems which illustrate some of these interactions. So here's this one theorem, which is due to Ivan Smith, maybe plus epsilon of new input from Jasper, Lander, and Alvarez Gavela, which says the following thing, that if you have a U of a manifold whose skeleton is a smooth manifold with a hyperbolic metric, then this implies that in fact x omega lambda is not an algebraic variety. So this means that if you remember the 3 examples I mentioned, x omega lambda is not in the class of the second example, algebraic varieties. However, in contrast, you could take the cotangent bundle of your favorite hyperbolic manifold, and this is certainly a Liouville manifold, as I mentioned. It's the first example. Another sort of theorem one could mention, which is much older, is that
the metric of the skeleton, the hyperbolic metric, is it something that comes from the original X or?
No. So, sorry, it admits a hyperbolic metric, so it's just kind of, there exists. You could, in fact, the same theorem is true if you were to ask the skeleton, if you were to say that the skeleton is a smooth, rationally hyperbolic. Yeah, I should say that the invariant that you use, so these Liouville manifolds have various invariants. The best known one is called Symplectic cohomology. Maybe an unfortunate name, but. And this is a invariant, which is essentially a graded vector space, and this is what you use to distinguish. Okay, I'm actually out of time, so I won't. The next example, the next theorem I would have stated was just to say that there's certain classes of contact manifolds which you can characterize, which can never occur as the ideal band of you certain infinity group. So I'll stop there.
Anybody have questions for the speaker?
In these complex examples, so you have this flow coming from the vector field. And does that somehow extend to an action of C star?
These complex examples.
Your second class of examples. Is there some?
I wouldn't expect so. Or I certainly don't see at the moment what this is.
The skeleton, they can have singularities, right?
So you can have very bad singularities, in fact. Typically, people focus on a particularly nice class of Liouville manifolds, which are called Weinstein manifolds, which have nicer skeleton. And yes?
If I'm talking about Hamiltonian system, like I have some kind of a classical mechanic system with Hamiltonian and a Hamiltonian flow, which I guess should be this kind of a symplectic system with the vector flow being the time being the push forward of the time. Would that be such a system? And if so, can you say something about the skeleton and the contacts? Or am I vague?
Often you will be bounded.
Well, I mean, you could have that this contact manifold, which appears, could be viewed as an energy surface for an autonomous Hamiltonian system. And there is sort of this interaction between the dynamics of the energy surface and what happens in sort of the interior. So in some sense, the contact manifold is a boundary of a compact symplectic manifold, which in this case has additional properties. And there's some interplay between the dynamics on the boundary, the Hamiltonian dynamics on the boundary, and the symplectic topology of the whole space, which is, for example, the symplectic cohomology captures this in some way. And I think this is, in some sense, a particular case of studying, given a contact manifold, study the fillings. How can I view this in different ways as a boundary of a compact symplectic manifold? How much does the boundary know about this? And then sometimes, of course, you have to restrict somewhat the compact manifolds you want to admit. And this particular situation, which he studies, allows a lot of interplay between certain data of this compact symplectic manifold and the boundary.
Thank you.
In the definition of the skeleton, do you require that the flow remains bounded or that it does not converge to infinity?
That does not. You could, for instance, require that it does not touch this canonically defined hypersurface. Somehow this will be equivalent because the view of flow, once you reach a certain area, once you reach this hypersurface, is just going to be it's completely canonically, it's explicitly described. It must, anything that reaches this hypersurface must reach infinity.
So the skeleton is compact?
Not in general, but this finite type assumption I added amounts to it being compact.
Any other questions? Let's thank the speaker again.